Okay, so we're going to take a look at a rate of change, and whoa, look at all those change moving at different rates. So that was 4 cents, and oh, wrong kind of rate of change. Okay, now before we can really get into our what we call related rates, we have to revisit derivatives for just a second because we don't also want to take the derivative with respect to the variable x. So what would happen if I've got a y equals 3x, but instead I want to take the derivative with respect to z? Well, the derivative of y would be 1, but then I've got the dy dz. The derivative of 3x would be 3, and then I've got to put the dx dz. And of course, 1 times dy dz becomes dy dz, and there I have an answer. The rate of change of y with respect to the rate of change in z would be 3 times as much of the rate of x changing with the rate of z changing. Let's take a peek at another one. Y squared equals 7 times x to the third power. Well, if I took the derivative with respect to z, y squared becomes 2y, and that is the change of y with respect to z. 7x to the third becomes 21x squared, and that is the change in x with respect to the change in z. Now, think about what we've been doing here before. You're like, what is this? Right? If we had y equals 5x squared, what would we do? dy dx equals 10x, right? I mean, that's what we do. Well, think about if I tried to show it this long, crazy way. Let's say, oh, the derivative of y would be 1, and that's the change in y with respect to x. And then the derivative of 5x squared becomes 10x, and that's the derivative of x with respect to x, or the change in x with respect to x, change in x. And say, hey, 1 times dy dx is just going to be dy dx. And of course, dx divided by dx cancels out. And there's dy dx equals 10x. That's why we've not had, a dy dx on both sides, right? We've had like a dy dx on one side, but we've not had anything like that on the other side because we've been taking the derivative with respect to that variable. If we're not taking the derivative with respect to that variable, then we've got this weird fraction involved. And of course, that's why we also wanted y equals, right? We didn't want y squared equals. We didn't want 5y equals. We just wanted y equals, because if you just take the derivative of plain old y, it turns into a 1. Okay, so let's see how we can put this into play. We've got a ladder, and it is leaning against a wall, all right? And the ladder is 10 feet in length. And where's my wall? I'm telling you, sometimes you just gotta build stuff yourself. Okay, so we got a bunch of concrete blocks that have been built into a wall. And we got Bugs Bunny climbing up that ladder. And of course, the bottom of the ladder is pulled away from the wall at a rate of 3 feet per second. There's Daffy Duck up to no good as usual. Daffy Duck is going to start pulling that ladder away from the wall, even though Bugs Bunny is still on that ladder. And Daffy Duck is going to go at a constant rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the base of the ladder is 6 feet from the wall? Well, let's get a slightly more accurate diagram, right? We're looking at a Cartesian coordinate system, so I got an x-axis, I've got a y-axis. The ladder is a line segment where one end of the line segment is on the x-axis, the other end of the line segment is on the y-axis. We got to get a little more room here, so let's get some of the silly stuff out of here, and let's rewrite that other stuff so it fits better. Oh, and hey, the Pythagorean theorem just showed up inside that triangle. Isn't that nice? Right? Because the x-axis and the y-axis are perpendicular to each other, we've got a right angle, so that's a right triangle. Okay, so we're going to need some type of equation to play with. Of course, I can use x as one side of the triangle. I can use y as one side of the triangle. And then, of course, I've got the hypotenuse, right? So the length of the ladder could be the hypotenuse, right? So wherever that ladder is hitting the x-axis, I'll use that x-coordinate. Wherever that ladder is hitting the y-axis, I'll use that y-coordinate. And then, of course, we've got the length of the ladder as the hypotenuse. All right, so because Daffy Duck is pulling the ladder away from the wall at a rate of 3 feet per second, let's take the derivative with respect to time. All right, so t is going to be the variable that I take the derivative with respect to. X squared becomes 2x, but then I got to put my dx dt. Y squared becomes 2y, but of course I have to put my dy dt. H squared becomes 2h, and I got to put my dh dt. Right? Each variable was taking the derivative with respect to time. Pythagorean theorem's got to come back into play again, because I've got 6 squared plus b squared equals 10 squared. Where's the 6 coming from? Well, I want to know the situation when the base of the ladder is 6 feet from the wall, so 6 will be my x coordinate. Where's the 10 come from? Well, the ladder was 10 feet, right? 10 feet in length, so that's where the 10 squared. Mystery number B, I don't know. What's that going to be? Well, let's figure it out. Hey, 8. When the bottom of the ladder is 6 feet away from the wall, the ladder is still reaching up 8 feet, right? That's kind of crazy to think about, because you're like, man, if the ladder is that far away from the wall, it's only a 10-foot ladder. Well, yeah, well, it still reaches up 8 feet, so that's kind of cool there. So I can plug in those values for x, y, and h, and do a little bit of simplifying. All right, so I actually have 12 dx dt plus 16 dy dt equals 20 dh dt. Now, do I know any of those rates? Actually, we know 2 of them. We know that the bottom of the ladder is being pulled away from the wall at a rate of 3. So dx dt is 3. And the rate of change for the hypotenuse? Well, the ladder is not going to change in length. It's going to be a 10-foot ladder no matter how I lean it against the wall, right? Unless I take like a sledgehammer to it and smash it and bend it. So there is no change. And so I can simplify this. Bum, bum, bum. Now, before I move on, you probably could have predicted that 0 a long time ago. Because instead of h squared, I could have put 10 squared, right? Because the ladder is always going to be 10 feet. So I could have started with x squared plus y squared equals 10 squared. And of course, the derivative of a constant is just going to be 0. And we could have had 0 right away. However, sometimes we have 3 different variables, and all 3 variables are changing. And so that's why I wanted to show it this way, where I actually took the derivative of that h squared. Let's subtract 36 from each side. So 16 dy dt equals negative 36. Divide by 16. I can simplify that fraction. Now, the problem is most folks, when we're talking about feet, are not going to expect an answer like 9/4. Like, what do you mean 9/4 of a foot, right? So 2.25 would make a lot more sense. Or if I said 2 1/4 feet, or if I said 2 feet 3 inches, right? But that's what 2.25 means. Oh, and there's a negative? Well, of course there's a negative. The ladder is sliding down the wall, right? The y coordinate is decreasing, right? As the x coordinate increases, the y coordinate decreases. That is why there's a negative there. So we're actually sliding down the wall at a rate of 2.25 feet per second. Bum, ba, ba. So there's our label, feet per second. So I'm going to give you a very, 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 very similar question with a ladder on a worksheet. What some hippie put this thing together. Look at that. State of Washington, east of the Cascades, Palouse Falls, right? Very, very arid area, but you know, sometimes a massive river cuts through there. In the case of this, fantastic, fantastic waterfall. It's really out in the middle of nowhere. I mean, you really have to venture out to reach this. If you attend college at WSU over there in Pullman, Washington, this wouldn't be too crazy far out of your way if you drove from like Seattle to Pullman and said, "Hey, can we stop and see the waterfall on the way, you know, back to college or the way home from college?" But most of us, though, it's like, you know, if we're gonna go on vacation, this is really out of most of where we find ourselves going, kind of real off the beaten path.